We're familiar with parabolas as the graph of quadratic equations. However, there are also geometric approaches to defining parabolas. Parabolas are actually a type of shape known as a conic section. Now, this name comes from the way that certain types of curves can be created by looking at a cone and intersecting it with a plane at various angles. So if we take a cone, and what we want to do is we really want to take a two-sided cone like this, then we can get various shapes out of this by intersecting planes with the cone at in various ways. So for instance, if we take a plane which is sort of parallel to the cone, then the shape that we get out of that is a circle. So a circle is an example of a conic section. On the other hand, if we angle this slightly, if we took a plane that looked something like this, then the shape that we got wouldn't be a circle anymore. It would be an ellipse or oval. Now, if we angle this far enough, then we'll get to the point that the plane is actually parallel to the sides of the cone. And when we do that, the shape that we get by intersecting the plane with the cone is a parabola. And then finally, if and this holds as we start angling these planes down. And then finally, if we were to take a plane that stood straight up, which I'll do in a different color because we've got all these going on. If we took another one that went straight up and down like this and intersected with the cone, then what we'd wind up getting is what's called a hyperbola, a curve with two different branches that go sort of in opposite directions as the green curves here do. So just by taking this two-sided cone and intersecting it with a bunch of different planes, we get a bunch of different kinds of curves. And the basic ones that we are most familiar with are circles, ellipses, parabolas, and hyperbolas. We're going to be focused on parabolas right now, and it turns out that they have another description in terms of the two-dimensional plane that winds up being very interesting itself. What we can do is the following. Let's take a line in the plane, any line at all, and then let's take any point not on the plane. And let me actually give these labels. Let me call the line L here and the point F. Now what I can do is I can consider all points x1, y1, where the distance to the point F is equal to the distance to the line L. Now, if we do that, then we can get some points out of that. So for instance, there's a point exactly halfway between F and L that is halfway between them, where the distance to F and the distance to L are equal, and this shortest segment goes in a straight line, and we call that point, we give that point the label V. This is going to be the vertex. And then there are lots of other points that we can find. So we could say this over here might be a point where the distance to the point F and the distance down to L are equal. And there are a whole bunch of these points, and it turns out that if you plot a bunch of them together, you will see that it is in fact a parabola. So these points form a parabola. And we have special names that we give to the line L in this figure, the point F and the point V. So L is called the directrix of the parabola. F is called the focus of the parabola, and V is called the vertex of the parabola. And we'll see some justifications for some of these names. First of all, the vertex is a term that we're familiar with from algebra as the highest or lowest point on the parabola, or in this case, when we don't have any axes involved, it's just the most extreme point on on the end of the parabola, the bell end of the parabola. We'll see at the end of the lecture why the point F is called the focus. It's actually for very good reason, which has a million different applications in the real world. The directrix, we're not going to be getting into the name of that so much. It's part of the definition of the parabola. So let's see how we can use some algebra to sort of see why the parabola that we're familiar with matches with the parabola defined by this geometric description. Okay, so now for convenience, let's align our parabola so that the vertex is the point 0, 0, and the parabola points upwards. Or, sorry, not, yes, yeah. So we'll put ourselves on the XY plane. We want to set things up so that the vertex is here at the point 0, 0. And it's opening upwards like this. And if we do this, then the focus is going to be a point somewhere on the y-axis. Now we're going to go ahead and give that point the coordinates 0, p. And if that's the case, then the directrix, which has to be as far away from every point on the graph as the focus is, has to be sitting down here with the equation y equals -p. And now we can see that the vertex 0, 0 is as far away from the focus F as it is from the directrix -p. But let's see what sorts of things we can say about other points on the graph. So if we take a point x1, y1 on the shape defined as being equally distant from the focus as the directrix, let's see what we can say about that. So x1, y1 is on the parabola, where we're defining the parabola in terms of the geometry, as on the last slide. If and only if the distance from x1, y1 to the focus 0, p is equal to the distance from the point x1, y1 to the line L. Now we can be more specific here because we actually know what the closest point is to x1, y1. Since we're going straight down from the point x1, y1 to the directrix, we know that this point down here has to be at the location x1, comma, negative p. Now we can use the distance formula here and say that, all right, well, these two distances can be calculated in the following way. So the distance from the point x1, y1 to the focus is x1 squared plus y1 minus p squared, whereas the distance from x1, y1 to the point x1 negative p is exactly x1 minus x1 squared plus y1 minus p squared. Y1 plus p squared. So we get, if we square both sides, we can simplify things. Also, of course, we know x1 minus x1 squared is just 0. If we square both sides, then we get that x1 squared plus, expanding this out, y1 squared minus 2y1p plus p squared is equal to, and expanding out the binomial term on the right, y1 squared plus 2y1p plus p squared. Now, there's a lot of cancellation to be done here. We have a y1 squared on both sides. We have a p squared on both sides. And so what we wind up with is x1 squared is equal to, we also need to add 2y1p to both sides. We get that x1 squared is going to be equal to 4y1p, or we could rearrange that to put the y on the other side. In fact, let me go ahead and do that. We get x squared is equal to 4p y1. And this is the equation of a parabola. In fact, we can see that this satisfies the equation y equals 1 over 4p x squared if we divide both sides by 4p. So what we see is that when we define the parabola this way, we get an equation for the points on the parabola that is a quadratic equation. And so we can see that we're really just describing the same shape two different ways, one geometrically and one algebraically with an equation. So this is what the equation of a parabola centered at the origin opening upwards looks like in terms of this number p. If we make p be a negative number instead, then what that's doing is it's shifting the focus down to the negative y-axis. In that case, the parabola will open downwards. On the other hand, if we exchange the role of x and y, then we'll get parabolas opening to the left or the right. So in summary, these are the four different situations that we can have for a parabola centered at the origin that has an opening either up, down, left, or right. So we have the equations x squared equals 4py, or in other words, y equals 1/4 p x squared. And there are two different forms that this takes. If p is positive, then we get this equation. So this is for p greater than 0. If p is less than 0, then we will get an equation opening downwards. In this case, or a parabola opening downwards. In this case, the directrix will sit above the parabola. Still at y equals negative p, but in this case, p is negative, so negative p is positive. And the focus is again at the point 0, comma p, but p is now negative. On the other hand, we could have the equation y squared equals 4px, or in other words, x equals 1 over 4py squared. And if we do this again, there are two different possibilities, and they're determined by where the focus is. So if p is positive, then that means that the focus is going to be on the right side. It's going to be at the point p comma 0. The parabola is going to look something like this, and the directrix will now be a vertical line with the equation x equals negative p. And then finally, if we're in the horizontal parabola setting, but p is negative, then the focus will be to the left of the origin at the point p comma 0. The parabola will open to the left, and the directrix will be at the equation, or will have the equation x equals negative p again. So we can describe a bunch of parabolas this way, and by using the fact that the equation can be written as x equals 1 over 4px squared or x equals 1 over 4py squared, we can determine the focus and directrix of parabolas that are given to us in these forms. Let's see an example. Let's find the focus and directrix of the parabola y equals negative 3/2 x squared. So the technique here is to always use the fact that we have the formula y equals 1 over 4px squared, where p tells you how far away from the vertex is the focus and is the directrix. So if y equals 1 over 4px squared, then that means that our coordinate 3/2, the coordinate of x squared here, is equal to 1 over 4p. Now it's just a matter of solving for p rather. If we multiply by 4p on both sides, then we'll wind up with negative 6p is equal to 1, which tells us when we divide by negative 6 that p is equal to negative 1/6. And that is enough to tell us the focus and the directrix. So the focus is going to be at the point 0, comma negative 1/6. We know it's at 0, comma negative 1/6 and not negative 1/6, comma 0, because our polynomial, or rather our parabola, is written in the form y equals an x squared term. Whatever variable in your equation is not being raised to the second power, that's the one that's the direction that you're moving in order to get to the focus and directrix from the vertex. So because y sits by itself in this equation, you're going to move in the y direction up and down. So the focus is at the point 0, comma negative 1/6, and the directrix is going to be at the point y equals negative 1/6, which is 1/6. Graphing out this situation, we're in the second case that we had last time, on the last slide. We've got the point 0, comma, negative 1/6, we have the line, y equals 1/6 as the directrix, and then the parabola itself opens downward like this. Actually, that was a little too high. Let me go like that. So this is how we can find the focus and directrix of a parabola that is centered at the origin. However, not all parabolas are centered at the origin, and in order to determine the focus and directrix of some other parabola, then we need to do some transformations. So let's start off by seeing how we would take a parabola with a given focus and directrix with vertex at the origin and move it somewhere else. Now let's look at what happens if we shift this whole figure to another point. If we shift this whole figure around, let me do things this way, so that the vertex is now at a point which I'll just label as h, k. Then let's see what's happened. We've shifted the origin, which was at 0, 0, to an x-coordinate of h and a y-coordinate of k. So we've added h and k to the points, to the point 0, 0. And we're going to do the same thing to the focus. The point 0, p moves to the point h, k plus p. And the directrix also gets shifted up, just like everything else does. And instead of being at y equals negative p now, it'll now be at y equals negative p plus k, because that's the amount that we've shifted everything vertically. Now, we have that the first equation that we had here has the equation x squared equals 4py. Now, in moving from the left graph to the right, we've moved h in the x direction, k in the y direction. And that translates the equation as well. And what it does is it replaces x with x minus h, where h is the amount that we've shifted horizontally, and it replaces y with y minus k, where k is the amount that we've shifted vertically. We can check to make sure that we've done this correctly, because if we plug h and k into the new blue equation here, we get a true equation. We get 0 equals 0 out of it. So that's a check that we've done things correctly. So if we have a graph that is has its vertex at some point other than the origin, we can expect its equation to look like this. Now, of course, this is not typically the way that you see the equation of a parabola look. Let's see an example. So let's find the equation of the parabola with vertex at the point 2, 4 and focus at the point 2, 5. So we've got our parabola, something like this, 2, 4, and 2, 5 as the focus. One of the things that we're going to need to identify is the number p. We have that our equation is going to look like x minus h squared equals 4p times y minus k. That's the equation of a parabola opening upwards or downwards. Upwards if p is positive, downwards if p is negative. P, however, is, other than the sign, is always the distance between the vertex and the focus, which we've seen before. So this is always the value p. So in our case, p is equal to 1 because there's a distance of 1 between the vertex and the focus. The h and k are precisely the coordinates of the vertex of the parabola. So h is 2 and k is 4. Thus, that means that an equation of this parabola is x minus 2 squared equals 4 times 1 times y minus 4. Now, of course, this is not the most common way that we actually see an equation for a parabola written. Usually, we see it all expanded out. So let's see what that looks like. Here. If we expand out the left-hand side, we get x squared minus 4x plus 4 equals, now I'm actually going to keep this 4 times 1 bit here looking like this because I want to remember that it equals 4p because we're about to write down a general way of seeing how these things work, and I want to keep track of what this term that came from 4 and p does. So we get 4 times 1 y minus, and then 4 times 1 times this negative 4. I'm just going to write that as 16. I'm only going to keep track of the 4p that's sitting here as a coefficient of the y. Now we can add 16 to both sides. Get x squared minus 4x plus 20 equals 4 times 1 y, which is 4p. And then we'll divide everything by 4 times 1, which is 4p. And we will get that 1 over 4 times 1 times x squared minus, and I'll simplify the rest of it, 4x over 4 is x, 20 over 4 times 1 is 5, and we get an expression like this. Y equals something times x squared minus x plus 5, which is typically how we see parabolas being written. So what this tells us is that parabolas have equations of the form, at least parabolas opening upwards. We'll write down the equivalent forms for them going left or right. Y equals 1 over 4p x squared plus bx plus c for some numbers b and c. So that's what upward opening parabolas look like. And in particular, this means that you can tell the distance, or you can compute the distance from the vertex to the focus of any parabola at all given in this form very easily just by looking at the coefficient of x squared and setting it equal to 1 over 4p. Let's see a simple example of that. Let's find the distance between the vertex and focus of the parabola y equals 8x squared plus 17x minus pi. Some ridiculous parabola like this that doesn't even have nice rational points to work on. So let's figure this out. We only need to look at the coefficient of x squared. This is what equals 1 over 4p, where p is exactly what we're asking for, the distance between the vertex and the focus of the parabola. So the solution to this is simply to take 8, set it equal to 1 over 4p, and solve for p. So if we multiply 4p on both sides, we'll get that 32p is equal to 1. Divide both sides by 32, and we get that p is equal to 1 over 32. So our answer is that there is a distance of 1 over 32 between the vertex and the focus. Now, of course, that doesn't exactly tell us where the vertex is or where the focus is, which we are usually interested in, but it does give us some information about the parabola. Now, we could do the same thing with parabolas opening left and right, and when we do all that, we come up with the following description of how the equations of parabolas can be looked at in order to tell what sort of parabolas they create in terms of their focus and directrix and vertex. All right, so a summary of what we have so far. We have parabolas that open upward. Their equation, we have two different forms that we use. We've got x minus h squared is equal to 4p times y minus k, or an equivalent rearranging of this. But we also see it in the form y equals 1 over 4p x squared plus bx plus c for some real numbers b and c. When this is the case, the vertex occurs at the point h comma k. The focus is at the point h comma k plus p. And the directrix is the equation y equals k minus p. So if we open upwards, if p is positive, we open downwards if p is negative. So the general picture of what's going on in this case is the following. We have our vertex at h comma k. We have our focus at the point h comma k plus p. And then we have our directrix at y equals k minus p. And if we can work out what p and h and k are, then we can describe the parabola entirely in terms of those numbers. I should have written here not necessarily open upwards. I should have said open vertically, and then specified up if p is positive and down if p is negative. Now, a similar thing happens for parabolas that open horizontally, but you pretty much just switch the roles of the x's and y's. So for ones that open horizontally, and that's going to the right if p is greater than 0, to the left if p is less than 0, we have the following forms of the equation. We have that y minus k squared equals 4p times x minus h squared, or x equals 1 over 4p y squared plus by plus c for some real numbers b and c. The vertex is at the point h comma k. The focus, now everything's horizontal, so the focus is actually at h plus p comma k. We're shifting things horizontally. The directrix will be at the line x equals h minus p. So very similar to what's going on in the first case, just horizontally. So in this case, we've got something like this, parabola here, vertex at the point h comma k, focus at h plus p comma k, and directrix at x equals h minus p. Now, what usually happens when we're given the equation of a parabola is that we're given an equation in one of these two forms. When that happens, then and we might be asked to graph that parabola, we need to be able to convert it into an equation of this form, because this is how we read off our h and k. Now, you can also use the vertex formula to get there. But I want to show you a technique that is useful in some other situations as well. So let's take the following example. Let's find the focus and directrix of the equation x equals 1 over 10 y squared minus y minus 1/2. Now, first of all, one thing we can note from the cases we had on the previous slide is that this parabola is going to open horizontally, either to the left or the right, and that's because x is the variable without any power of 2 on it. Now, the first thing that you want to do is you want to multiply or divide both sides of the equation by something in order to get the coefficient of y squared to be 1. So we want to, in this case, multiply by 10 to get the coefficient of y equal to 1. So we'll multiply both sides of this equation by 10 and get 10x equals y squared minus 5y minus 5. Now, what our goal, I'm sorry, minus 10y. That was silly of me. What our goal is to make this look like something of the form 4p times x minus h equals y minus k squared, to make it look like one of the, or the form of the equation on the last page that gives us the most information. This gives us h, k, and p, which allows us to determine the directrix and the focus. So let's go ahead and keep working here. The left-hand side looks okay. We've got something times x. That's approximately what we want to happen over on the left. On the right, we need that to be a perfect square. And currently it's not. Y squared minus 10y minus 5 is not a perfect square trinomial. However, we can use a process called completing the square to get there. The first thing that you want to do is to get all the y terms, y and y squared terms by themselves, get rid of the constant terms. Now, what we want to say is, what would we need to add to the right-hand side in order to make it a perfect square trinomial? And the thing that you want to add is 1/2 times let me write it as b over 2 squared to both sides, where b is the coefficient of y of the single it's the term with y raised to the first power. Now in this case, b over 2 squared is equal to negative 10 over 2 squared, which is negative 5 squared, which is 25. If we add 25 to both sides of this equation, then the right-hand side is in fact going to become a perfect square. So we end up with 10x plus 30 on the left equals y squared minus 10y plus 25. Now, when we go to factor the right-hand side, it will become y minus 5 squared. And so it's starting to look a whole lot like the equation that we're aiming towards. On the left, we want to factor out whatever the coefficient of x is. So in this case, we'll factor out a 10, get x plus 3 left, and now we have in fact gotten an equation that matches what we were looking for. This equation is equivalent to the one that we started with. Its graph includes all the same points, but it is now in a position that we can figure out what all the different pieces are. So now we have that 4p is equal to 10, h is equal to negative 3, and k is equal to 5. Remember, in the formula, we have x minus h and y minus k, so the h and k appear with signs opposite that they do in the formula above. So this tells us that the vertex of this parabola is at the point negative 3, 5. Furthermore, if we solve for p, we get that p is equal to 5/2. Now, because everything is opening horizontally, this p is going to get added to the x-coordinate of the vertex in order to get the focus, and subtracted from it in order to get the directrix. So the focus is going to be negative 3 plus 5/2, 5, which gives us, let's see, negative 3 is negative 6/2, so negative 6/2 plus 5/2 is negative 1/2, 5, and the directrix will be x equals negative 3 minus 5/2, so we'll get x equals negative 11/2. So that gives us the information asked of us in the problem. Let's go ahead and take this information and graph the equation. Sorry. So I like to start with the vertex. The vertex is at the point negative 3, 5. We have that the focus is at negative 1/2, 5. So that tells me that the parabola is opening to the right. The parabola always opens in the direction of the focus. And then the directrix is going to be at negative 11 halves, which is almost, or is halfway between negative 5 and negative 6. So here's x equals negative 11 halves, of course, because it's a vertical line. And then our parabola looks something like this, consisting of all the points that are equally distant from the focus and the line x equals negative 11 halves. We can, of course, go the other direction as well and find the equation in sort of expanded form of a vertex given information about its either its vertex and its focus, or its vertex and its directrix, or its directrix and its vertex. Any two of those pieces of information is actually enough to determine the equation of the parabola. So let's see how that goes. Let's find the equation of a parabola with focus 2, negative 6 and directrix y equals 8. So to help us out here, let's sketch things out. It's usually a good idea to do so anyway. So our focus is at 2, 3, 4, 5, 6. You'll notice I'm not being super precise here. That's because this graph is just to organize our thoughts, make sure that we've taken things into account properly. So there's our directrix, and then our focus is way down here at the point 2, negative 6. So from this, what we can see is that, broadly speaking, our parabola is going to look something like this. It's going to pass between the focus and the directrix. It's going to be curved in the direction of the focus. And so the question is, how do we get the equation? Now we're going to use the fact that from this we can see that the parabola is opening vertically. In particular, we can see it's opening downward, but we'll see that in a second. And so we can use the equation x minus h squared is equal to 4p times y minus k. Now, in order to do this, we're going to need to know h, k, and p. Now, currently, we don't have any of those, but we can figure them out. And the reason we can figure them out is because we know that the vertex is always halfway in between the focus and the directrix. So the midpoint of this segment is the vertex. So we know that this point up here has an x-coordinate of 2 because it's sitting right above the focus, and it has a y-coordinate of 8 because it lies on the line y equals 8. And so now all we need to do is figure out the midpoint of the of the points 2, negative 6 and 2, 8. Well, it turns out that the way to do that is to take the average of the x-coordinates and the average of the y-coordinates. So the average of 2 and 2 is 2. The average of 8 and negative 6 we get by adding them together, which gives 2, and then dividing by 2, which gives 1. So the vertex of this parabola is actually at 2, 1. So that helps us out. So the vertex is at 2, 1, which is the h and k in our formula. And then P is the distance from the vertex to the focus, or equivalently the distance from the vertex to the directrix, or equivalently half the distance from the focus to the directrix. Any one of those ways can help you work it out. In this case, I think it's easiest to see that because the vertex is at 2, 1, and the closest point on the directrix is at 2, 8, the distance from the vertex to the directrix is 7. So in this case, the value of P is 7. Thus, we have that x minus 2 squared is equal to 4 times 7 times y minus 1. And now this is an equation of the parabola given here, but if we want to express it in the more typical form with y by itself, then we can simply by expanding all this out. So we get x squared minus 4x plus 4 is equal to 28y minus 28. If we add 28 to both sides, then we get that x squared minus 4x plus 32 is equal to 28y. Now if we divide everything by 28 and rearrange things so that y is on the left, we get the equation y equals 1/28 x squared minus 1/7 x plus, we can reduce those by 4, so we get 8/7. So that is, in standard form, the equation of the parabola with a focus at 2, -6 and directrix at y equals 8. All right, so these are how we handle parabolas in terms of directrices and foci on the plane. But the question remains, why do we do this? Why talk about the focus at all when we are familiar with quite familiar with parabolas from algebra that we've done in the past? And a big reason for that is the following result, which we're about to look at. It turns out that every time you see a satellite dish, or even the inside of a flashlight, they usually make shapes that are paraboloids, which are the three-dimensional version of a parabola, what you get by spinning a parabola around. Let's see why that is. So what I want to do is look at the following setup. I want to take a parabola here, and it's got its focus here at 0, p. I'm going to go ahead and set it up with the vertex at 0, 0. Make it a little bit simpler than we had just recently. And I want to look at some particular point on here. I'm going to label it x1, y1. And then I want to think about some sort of signal coming straight in like this. So this is thinking about this as being, say, the graph of the surface of a reflector dish, like a satellite dish. And it's pointed at some signal, and the signal's coming in, and it's going to hit the back edge of the bowl here, and it's going to reflect off. Well, which way is it going to reflect? Physics gives us an answer here, and it tells us that if we set up a line here that is just tangent to the curve of the parabola, meaning it just barely touches the parabola in one point and matches the sort of instantaneous slope of the parabola at that point, then it's going to reflect off in such a way that the angles formed between the incoming signal and the red line is going to be equal to the angle of the after it bounces off. So these two angles are going to be equal. Now, what I want to do actually is to look at what happens if we don't assume that they're equal and instead just look at this segment right here. And I want to see how we can compare the two angles here and here. I'll make them the green angle and the blue angle. Both of those are being made with the red line. Now there is one piece of this that unfortunately I'm going to have to punt to calculus. From calculus, we can actually figure out what the slope of this line is. Now, we have that this curve has the equation x squared equals 4py, or y equals 1 over 4px squared. And it turns out that when that you can use some principles from calculus with this to determine that this line, the red line here, has slope equal to equal to x1 over 2p. This depends on x1, so as you move further away from the origin, the slope gets steeper and steeper and steeper, which should hopefully be intuitive, but we can get a formula for the slope of this line pretty easily. Now what I want to do is to use some vectors. I want to use some of the principles from vectors that we had, and we actually know how to calculate these two angles, the green angle and the blue angle, using dot products. So let's recall that we have that the cosine of theta, where theta is the angle between two vectors, is equal to the dot product of those vectors divided by the products of the magnitudes of those vectors. So what I want to do is to get a vector to get 4 different vectors pointing in the various directions that we're looking at here, 2 of them going along the red line, 1 of them pointing straight up, and 1 of them pointing from the point x1, y1 to the origin. Sorry, not to the origin, but to the focus. And then furthermore, I'm going to go ahead and sketch in the directrix here, because that's going to wind up being important to us or helpful to us in our computation. So I've got the directrix here, and remember that the directrix has the equation y equals -p. All right, so we would need a vector in each one of these directions. Well, let's start with the easy one. One of these vectors here we can write as just the vector 0, 1. That's the unit vector pointing straight up, and that'll be one of the vectors that I use to compute the green angle. Now, for the red angle that's going to go along with, for the red vector used to compute the green angle, we want a vector that has a slope of x1 over 2p. Well, the easiest way to get that sort of vector is to just take a first coordinate of 1 and a second coordinate of x1 over 2p. However, using fractions is actually a little bit of a pain, so it's going to be even better for us to use the vector 2p, x1. this vector still has a slope of x1 over 2p because the slope is computed by taking basically the y-coordinate divided by the x-coordinate. And so to compute the green angle, we're going to use these two vectors, 0, 1 and 2p, x1. Now for the blue vector, we're going to, for the blue angle rather, we're going to take another red vector. It still needs to have a slope of 2, but it needs to be going in the opposite direction from the one we just did. So we'll get that as negative 2p, x1. That's our third vector. And then our last one is the vector that goes from the point x1, y1 to the point 0, p. And this one's going to be the most complex that we've got. But we know that we can compute the coordinates of a vector simply by taking the differences of the first coordinates and then the differences of the second coordinates. So going from an x-coordinate of x1 to an x-coordinate of 0 is negative x1, and going from an x-coordinate of y1 to, or a y-coordinate of y1 to a y-coordinate of p gives p minus y1. So that's the vector from x1, y1 to the focus. Now let's see what we can conclude about these various angles, the green and the blue. And let me go ahead and give them names now. I'll call the green one alpha and the blue one beta. So let's see what we can say. We can say that the cosine of alpha is equal to the dot product of 0, 1 and 2p, x1 divided by the magnitude of the vector 0, 1 times the magnitude of the vector 2p, x1. So let's do that. The dot product on the top is as follows. We take 0 times 2p, which of course just gives us 0, and then 1 times x1, which gives us, well, x1. The magnitude of the vector 0, 1 is 1. It's a unit vector. And then we've got this magnitude of the vector 2p, x1, which I'm going to leave that way. So we wind up with x1 divided by the vector 2p, x1. So the magnitude of the vector 2p, x1. So that's what the cosine of alpha is. Now let's look at the cosine of beta, which is going to be a little more complicated. Cosine of beta is going to be equal to the vector negative x, p minus y1 dot product with the vector negative 2p, negative x1. Oh, and I just realized I forgot to put a negative on that vector there. Sorry about that. That was probably confusing. Divided by the magnitude of the vector negative x, p minus y1 times the magnitude of the vector negative 2p, negative x1. So let's go ahead and do this. The dot product on top will give us negative 2p x1, and then plus, but there's a negative from the x1 coming along, so we'll write minus minus px1 plus x1 y1. Oh, first one should have been positive because you got a negative times a negative, of course. All right, so then again, I'm going to, actually there's a couple things that we need to do with the denominator. The first one is to note that the second term in the denominator, the magnitude of negative 2p, negative x1, is actually the same as the magnitude of the vector 2p, x1. They are vectors equal in magnitude, They're just pointing in different directions, but they're completely equal in magnitude. One is just a scalar multiple of the other by -1, which doesn't change its length, doesn't change its magnitude. But the other more important thing is to note that the magnitude of -x1 comma p minus y1, actually writing that out using the formula would be quite complicated. And so that's this distance right here. However, here's where we can use the fact that we're on a parabola, which means that this distance from the vertex to the point x1, y1 is equal to the distance between the point and the directrix. And the distance between the point and the directrix is exactly y1 plus p. It's a distance of y1 from the point down to the x-axis and a distance of p from the axis down to the directrix. So that means that we don't have to go through the whole process of expanding all that out, working it all out. It's simply y1 plus p, and we know it is. Now, let me go ahead and I don't want to make things more cramped than they need to be. So let me go ahead and take some of this and put it on another page. And we'll go back when we need to. All right, so this is what we have so far. So continuing with computing cosine of beta, we have 2px1 minus 2px1 gives us just px1 plus x1y1 in the numerator. And then we have y1 plus p times the magnitude of 2p comma x1. We have an x1 common factor on the top, so we get x1 times p plus y1 divided by y1 plus p times the magnitude of 2p x1. And wouldn't you know it, there's a common factor. y1 plus p can cancel, and we're left with x1 over the magnitude of the vector 2p comma x1. But you'll notice that this is exactly the same as we got from before. So we have that cosine of alpha is equal to cosine of beta. And furthermore, alpha and beta are between 0 and pi, and cosine is 1 to 1 on that region. And therefore, that means that alpha has to be equal to beta. This is huge. What this means, as we see from the diagram on the previous side, that when a signal comes in down straight onto the edge of a parabola and bounces off, it's always going to hit the vertex. Sorry, not the vertex, the focus. This is indeed where the name focus comes from. If we draw another page and illustrate what's going on, if I've got a parabola with a focus, say here, then what this means is that no matter what signal, or no matter where my signal comes in, as long as it's coming straight down and is aligned properly, as long as the parabola is focused towards, or is pointing directly towards the source of the signal, then all of the signals that come in are going to be bounced straight to the vertex. So the way that this applies in real life, we've got a couple of examples that I mentioned before. When you have a satellite dish, it's pointed at a satellite that's sending out a bunch of information. Now, that information is individually, or over any small area, pretty weak. As the signal goes out, it spreads and it dissipates. But what happens is if you take a satellite dish And all it has to be is reflective, nothing fancy going on inside the dish, as long as it's made in the shape of a parabola or paraboloid, technically. Then as all the signals come in, you've got 3 feet diameters worth of signal that all gets bounced in and focused at one single receiver that might only be an inch or less across. And so that boosts the signal dramatically. All of a sudden it's detectable, and you can actually get something with it. You can get a satellite signal. This has been used for telescopes. If you point a great big reflector dish at, say, the night sky, then as the light comes in, it's going to be gathered all together into a single point, and you can maybe see things that are very, very dim that you couldn't see before. Going the other direction, if you were to put, say, a light source at the focus of a paraboloid and have it shine, then the light would go in all sorts of directions, but all the light that hit the parabola surrounding it would then all bounce off in the same direction. And this is what allows very, very powerful flashlights to be made. It's not that they're creating some sort of laser that focuses the light in one direction. That's a different process entirely. But they're creating a very bright light and then using a parabola to focus all of that in the same direction. So parabolas, curved dishes like this have been used for a long time for precisely this purpose. And it can allow you to detect things that are very far away. And it's one of the biggest applications of parabolas and their properties that we see all around us all the time. So let's see an example of how we might use this idea to solve a problem. A satellite dish is 4 feet across and 1.5 feet deep. A parabolic satellite dish is 4 feet across, 1.5 feet deep. Where should its receiver be placed? To capture the signal. All right, so let's sketch out our situation. So we have a parabola here, and we're told some information. We're told it's 4 feet across. So that's 4 feet. Let's erase the extraneous here. And then we are also told that it is 1.5 feet deep. And we want to know where we should put the receiver. Now, what we want to do is to set up a coordinate system to help us out with this. And it's always easiest to set up your coordinate system with the vertex of your parabola at the origin, if possible. So let's set up a coordinate system here, x and y. And so we know that this system has a formula of x squared equals 4py. Now, this p is going to tell us where the focus should be. The focus should be somewhere along the y-axis, but we want to know how far up it should go, how far away from the center of the satellite dish it should go. For that, we need to figure out p. Now, in this situation, our equation only has one unknown parameter, this p in it. And so to figure out what that is, we can simply take one point other than the origin that we know is on the graph, plug that into the equation, and solve for p. So for instance, in this setup that we have here, we know that this point right at the edge of the parabola has coordinates 2, 1.5. The parabola is going to be symmetric around the y-axis, and so it's going to go from an x-coordinate of -2 to a y-coordinate of 2, and so we know that the point 2, 1.5 is on the graph. Meaning, if we substitute these values into the equation, we will get a true statement. So let's plug in x equals 2, y equals 1.5 to the equation. If we do that, then we get 2 squared is equal to 4 times p times 1.5. We know this has to be true because this point is on the equation of the parabola. So we get that 4 is equal to, now 4 times 1.5 is 6. And so solving for p, we get p is equal to 4 divided by 6 is 2/3. So that tells us that the focus should be 2/3 feet up from the center. Or, as you would probably state it, 8 inches. So our answer might be something like 8 inches above the center. And if you put the receiver 8 inches above the center, then you're guaranteed that all of your signals will get to your receiver. One advantage of this also that I didn't mention is that all those satellites that you aren't pointed at won't get focused in. The parabola, the satellite dish here will only focus signals in from something it's pointing directly at. If there's some other signal that comes in randomly here, it's just going to bounce off, do something else. It's not going to go towards the focus. The only signals that are going to be reflected into the focus are the ones that are coming straight in the first place. So that's why satellite dishes and flashlights and all these other ways that we have of focusing information into a single point, or taking a source and expanding it out all in one direction, uses the parabola. It does exactly what we need it to.